So hello, my name is Marcus Matheson. I'm part of Senior Design Group 2, number 20, and we're Design Group Hot Jam, and our project is Better Water for a Better Beer. This is our abstract, and actually everything I say here, you can find out much more information at our website. You can see it's our Google site, sites.google.com/a/temple.edu/brewwater. This video will also be on there. Other things that we want to feature will also be on there. So this is our group. This handsome fellow right here is myself, and I'm joined by another environmental engineer student, Nicholas Hoffman. Andrew Stackhouse and Jason Wolf are our mechanical engineers, and our faculty advisor is Dr. Robert Ryan. So the whole idea behind our project is we started this just because homebrewing really kind of exploded in the past decade or so. And I know I was talking to another friend of mine, an engineering student at another school, and he mentioned, you know, you're an environmental engineer, and we wanted to do something involving the homebrewing process. So we decided we should focus on the water. It's something that, 90% of whatever goes into the beer, by mass is water. It's definitely a huge component of it. And we also feel like we could create a system to kind of help out homebrewers and kind of help tweak what their homebrewing process. Just provide another skill, something else that they could kind of tweak. And so what we ended up doing was we did some research, and we also found out that not all waters are created equal. So if you have really hard water, for example, it typically can be very hard, and you also may want to just change up a recipe using the water and to getting the results that you want. So this is our basic project overview, and I'll kind of explain this a little bit more in our next diagram. So our system layout that we have basically starts out at the controller, or on the controller, at the computer, is the graphical user interface, also known as the GUI. And this is very simple. It's just kind of where you're going to graphically see your water profiles that you want to go ahead and select. And all you do is really hit the start button. The information is then relayed automatically to the controller. The controller will then send the signals that we already programmed to the solenoids and the pumps. Solenoids are going to be connected to a deionized water reservoir that will continuously flow in water. And the solution reservoirs, we have 6 of them. Each will be connected to a pump. They will run sequentially. And dissolved in each of these solution reservoirs are going to be one of 6 brewing salts that we're using. The pumps and the solenoids will basically connect directly to the mixing manifold, where it will discharge into the float sensor. Float sensor will just be manually overridden, so whenever it hits the actual amount of volume that we would like, it sends the information back to the controller, and it shuts the system off. Here is kind of our testing. We're testing our design right here. As you can see, here's a computer that the user will provide. On it is our program, and this is just kind of like our motors in one of our solution reservoirs. This is Andrew. He's about 6'5" to give some frame of reference, and he's holding up kind of our power supply and our controller system. Right here we have the deionized reservoir. Down here is the final created water reservoir. These are our pumps, or I'm sorry, these are our pumps right here, and these are our solution reservoirs. Obviously they can be scaled up depending on how much we decide to add, or also with the solubility I'll get into in a second. The length of it is about 1.5 feet, so that seems pretty good. And again, everything's pretty much waterproofed whenever it's actually running. Very important. Again, get to that a little bit later. So these are our technical design constraints. We wanted to make sure that we were creating the water that we're advertising. So whatever water profiles we decided on, we said we want to create the water 10%, within 10% of those values that we chose. But again, we also want our system to be accurate and reliable, consistent, really. So accuracy and consistency were the huge things we're looking for. Head consistency more refers to our solution reservoirs. So the solution reservoirs that we have, we just wanted to make sure that the flow was going to be consistent out of them. The pressure can change depending on the height of water inside of them. So again, having a solution reservoirs that will deliver a consistent amount of flow, regardless of the amount of water inside of it, is important. Flow rate was more of a pump design constraint that we had, and we just basically wanted to make sure with that is that we had a certain size of tubing. We wanted to make sure that we were delivering as much fluid as possible through this tubing and kind of minimize the air bubbles so that, again, accuracy and consistency. Energy output consistency is the same thing. We just want to make sure that our energy output values didn't vary by more than 5%. It's kind of a ballpark figure, but again, the draw on the energy could force the motors to move faster, and we didn't want that. Operation time, that's an arbitrarily chosen value. We just chose 10 minutes. We thought that that was pretty reasonable for an initial design. The non-technical design constraints include manufacturability. We want to use universal software, so users regardless of your operating system can use it, Linux, Mac, PC, whatever. Manufacturability, again, I kind of mentioned this before, but we want to make sure that you can add on more if you wanted to. You can brew more, you can brew less, something that you can certainly tweak with as time went on. Sustainability, you buy something, we just want to make sure that it's something that you can use over and over and over again. The total cost, this kind of more has to deal with line with our budget constraints that we had. Senior design allots each group about $500, so we decided that's a point that we wanted to stick to. And then health and safety, again, you have water, you have electricity. We want to make sure that we waterproofed everything, so we made sure that the water and electricity stayed separate. So when determining the water profiles, we use 6 very common brewing salts: Epsom, gypsum, calcium chloride, canning salt, baking soda, and chalk. Anybody who is kind of familiar with chemistry a little bit knows that each salt is not just composed of one element or ion; it's composed of 2. So whenever you're adding any one of these salts, in our solution reservoirs, you're going to be adding 2 of these ions. So it can be kind of tricky to say, this is the profile that we want, but how do we get that? So we ended up using a MATLAB program we created to kind of fine tweak and see what values would work for us, and kind of see like a range of different values that might work for us for these water profiles. Solubility also was very important too. Just because you can calculate how much salt or how many ions you should get out of a solution doesn't mean necessarily that the salt will provide it, just because of the solubility in each reservoir with each salt. The biggest problems coming with gypsum, which is actually the larger of the solution reservoirs that I pointed out, and chalk. Chalk I will talk about right now. Chalk actually has an extremely low solubility of 15 milligrams per liter. This is pathetic for a concentrated solution that we want to use in our reservoir. So we looked at how we could increase its solubility. We came up with the idea of using phosphoric acid. This is something that actually does not alter taste. We had this confirmed by a couple of brewmasters that we interviewed. And it does not alter the taste, it doesn't affect the yeast, and it's something that you can drink. It's fine to drink. It's in Coke as a preservative agent. And what happens is it will have calcium carbonate, and the phosphoric acid will react to form semi-soluble calcium phosphate. And the calcium phosphate we thought was going to be a little bit more soluble than what we ran in our tests when we eventually did use this. And it wouldn't dissolve. So we actually ended up having precipitate form in there, which we didn't want to put in our solution reservoirs for fear of clogging. This is a problem that we actually did not solve by the time of our testing. So it is something that we would look forward to solving in the future. Testing these ions, once we have our water profiles tested, we want to make sure that we are getting the right results. Our metals were tested through a process called AAS, the Atomic Absorption Spectrophotometry. And Hotch test kits tested our chloride and our sulfate ions. These guys you can pretty much find in a lot of different labs. They're very easy to use. You just kind of buy a pre-made test kit. The AAS, here's an example of a calibration curve, our standardization curve that will help us basically analyze our water. You get certain standards and you measure them at known concentrations. And then from there, you just kind of test your water sample. This is actually a really good calibration curve that we ended up having. So we just wanted to make sure that we showed that one. It's for calcium. Titration is a really straightforward procedure. What you do, as long as you know the strength of the acid that you're adding and you know the volume of the water that you're going to be titrating into, there's a standard equation that you use. We had all this set up at the Allentown water filtration plant. They have a standardized acid solution, so we knew exactly what we were going to get into when we needed to test our alkalinity. So these are the final water profiles that we ended up with. We ended up with 6 total water profiles, 9 if you include the alternates. So what happened was, just to kind of explain this, we have a Vienna B and a Burton B. While using our MATLAB program and figuring out the solubility and such, we found out that we were really having a problem with sodium. And the sodium was a little bit too high for the water profiles that we wanted, so we were afraid that it was going to mess up the flavor. It wasn't going to give us what we wanted. But we figured that the higher sodium content would be fine for baking applications, since salt is used when making things like bread anyway. So we labeled it B for baking, and we just left it just as it is, Vienna and Burton, for the brewing applications. Now the values are very different, but that's because we looked at a measure called residual alkalinity. Typically in the brewing process, you boil your water, and there's a lot of ions that end up precipitating out, and they kind of take away from the alkalinity. Well, residual alkalinity is how much alkalinity is actually used in the water that you're brewing with. So we ran some calculations for residual alkalinity, and we adjusted the ratios accordingly. A lot of eyeballing going on, but in the end, we thought that these numbers were very close to the different water profiles that we found, and matched in general most of the sources that we found for these water profiles. So our salt reservoirs, very simple. We wanted to make sure that, again, they were very consistent and accurate. Make sure that they didn't react with any of the salts that we put in there. They were easily refillable and sealable, and the design that we found was the Marriott's bottle. It fulfilled all these requirements. The Marriott bottle is different from a normal reservoir that is open to the atmosphere, where the amount of pressure depends on the height of the water. As the water goes down, the head decreases, and basically the flow rate is changed. It goes a lot slower when there's less water inside of the tank than when there's more. At a Marriott's bottle, it's only exposed to the atmosphere here and down to a certain level that's above the exit tube. What happens is that regardless of what height the water is at, the water should exit at the same flow rate. This can be solved using Bernoulli's equation. So in order to save on costs, we ended up using PVC pipe. We used 4-inch diameter PVC pipe cut into about 1 foot sizes. Again, this can be adjusted accordingly. And basically a PVC reducer, borosilicate tube, expanding rubber plug, and barbed hose fittings. And the borosilicate tube actually was an important piece because when we initially tested our flow rates for these, we found out that we'd have to fill the bottle through the bottom. And so we'd tilt it over upside down, we'd fill it up with water, and then we'd seal it, and then we'd re-invert it. And the problem that we were having with our initial flow rate testing is that water would enter this borosilicate tubing. So we discussed the problem a little bit and found out that, or we just kind of decided that we wanted a check valve installed at the bottom. The check valve would make sure that the flow of air from the atmosphere would come into the tube, but no water was going back up into our borosilicate tubing exposed to the atmosphere. We were just again, we were getting inconsistent flow rates, and we just wanted to make sure that we weren't having any water enter that tubing. Unfortunately, the check valves had too good of an effect, and we actually weren't able to have any discharge unless there was a suction force pulling at our check valve to let some air into the salt reservoir. So what we did is we ended up running a much lower flow peristaltic pump, one that we borrowed from a lab here, and we ran them a couple of 1-minute tests, and we got values that were within 10% of each other for the mass that was discharged. And we decided, since we're going to test our final pumps with this and not just a much slower pump, we decided that our Marriott bottles worked out pretty well. They got us pretty reliable results for the time period that we ended up using. This is our graphical user interface. This is the final design of what it looks like. So it's very easy. You just select the water profile from Vienna or London, and then you just hit start. It uses the processing software language, which is cross-compatible with whatever operating system you decide to end up using. It basically sends information to the controller, which we used an Arduino Uno microprocessor, and it only has 2 states, running and a ready. So it's going, it's running, or it's ready, it's waiting. The solenoids that the controller discussed, or that it communicated to, it went between a trickle flow and a high flow. Trickle flow is when all the pumps are running, and then the high flow is basically just to top everything off once the ions had all been delivered in the solution. And then the float sensor, again, it's manually. We made sure we had some sensitivity in there, but not too much. But we programmed that to make sure that once it hit, we programmed it for originally an 8-gallon batch. Once it hit 8 gallons, it shut off. Power supply, nothing much, just an 12-volt AC/DC power converter. And so with the software, what we ended up doing to make sure that we were getting the results that we wanted to, we ran multiple dry runs with empty reservoirs just to make sure it was turning in the time span that we wanted to. And we had some problems. The one that stands out the most was we had an EMP pulse that happened once the system was done running, and it would just kind of shut off the system, which wasn't too much of a problem since we were done. But if you wanted to run more than one batch at a time, or sequentially, you'd have to turn on the system and everything. But we ended up solving that problem. It wasn't too difficult. But in general, the malfunctions were fairly easy to solve. So with the energy output, we wanted, in order to test this, we wanted to hook up 6 motors with their loads. So we wanted to make sure the salts were connected with the solutions inside of it, and then have the system run basically. And we wanted to run those for 5 minutes and record the current every 50 seconds or every 30 seconds to make sure that we had, again, the consistent flow rate. The mechanical systems, we decided to use peristaltic pumps for our pumps of choice. This is just because each turn that they should have delivers a very discrete amount of fluid to our system. So we used a 6x6-inch block as the housing and a 4-inch diameter circular plate to kind of turn our tube. And the motors that we decided provided about 200 Newton centimeters of torque, just enough to make sure we were moving the water that we wanted to through the system. The mixing manifold, this is just a fancy way of saying it was a PVC pipe put on an angle. Gravity did all the work for us. So during the actual testing of our mechanical system, we used actual loads of just like deionized water. Our current draw, the good news is that it was much lower than expected. We definitely were not drawing as much current or as much power as we thought we would. But unfortunately, the 5-minute time span, and this is what happens when you have a restricted budget, we didn't have quite good enough motors, and so running them for 5-minute intervals was too much stress on our motors. And what happens is 3 of our 6 motor gearboxes failed. So at the end of the project, we actually only ended up having 3 motors that still worked functionally. And then the pumps themselves were also experiencing issues just because this had been about our second or third iteration of these pumps. And the pumps were physically pulling the tubing through them, not just the water. And because of this, eventually what happened was it would pull so much tubing through, it'd run out of tubing, and then when it couldn't pull out anymore, the system would just kind of stop. So our actual flow rates are still unknown. But the idea behind what we were planning on doing was basically we just wanted to, again, run each 4 as long as we could. We were able to get our discharge up to a minute with each of the motors running, and then basically just see what the mass was that each of the pumps was able to pull through the mass of water. Knowing the temperature, we could find out the density, and then we could basically find out the volumetric flow rate. So again, this are our 1-minute flow rates, much lower than the 5-minute flow rates they originally intended. The motors really varied. They varied by quite a bit. Number 2, the percent variance was only about 6.21%, which isn't so bad. But then when you get to motors 4 and 5, it's close to around 20, and that's very inconsistent. And it just kind of shows that for one of the runs we had like 103 grams being discharged, and then the next one we had 85.4. So our pumps, we experienced a lot of issues with those, and the motors, the quality of these motors that we ordered clearly started to come through in our testing. Our cost analysis, we did have a lot of materials that were donated, but I think that overall we did adhere to the budget. We had our original intent was $500. We spent $507, so I think that in this way it was considered a success. So in summary, error minimization, unfortunately, we weren't really even able to test the ions just because we weren't able to get consistent results from our pumps. So we really weren't able to get the consistency and the reliability to say that our error minimization is below 10%. Our head consistency, I think, again, this refers to our solution reservoirs. I think that was very successful. We tested this with just a much slower rate peristaltic pump, but we were able to find that it had pretty consistent results, especially with the check valves. The flow rate, again, this is because of the motors, we weren't able to get the flow rate that we wanted to. The energy output consistency, because the pumps were also very inconsistent, we weren't able to check that at the time of this presentation. And the operation time, of course, we weren't really able to finish at this time just because of everything else not being able to work. But our non-technical design constraints, we thought that we were very successful. We did actually end up creating this software, which is amazing. Being that we wanted to do this one thing, and it was able to do that very, very easily. You just select it and you hit start. I consider that a major success. It's definitely scalable. Again, we can adjust either the system or we can adjust the solution reservoirs to deliver as much water as we want. Reusable and modular, we could sit on our model at the end of it. So we like to think that it's very reusable. The cost, again, $507 as opposed to $500. I think $7 over budget is not bad at all. And of course, the separation was never really an issue for us. We made sure that all of it was waterproof and that it was going to be safe when we were running it. The final modifications that we ended up making after our original presentation was that even though 3 of our motors were gone, we could still test 3 of our solution reservoirs. And so we kind of chose 3, the metals basically, in the AAS unit. Unfortunately, also due to the time constraints, we were having issues calibrating our curve for our atomic absorption research. And unfortunately, we only really got the values for calcium. So we wanted to test 2 to 3 predicted ions, but we only tested the calcium. And the results were mixed. We noticed that basically as the calcium needed increased with each of the higher, the more concentrated water profiles that we had, the error was starting to increase with that. So if it runs for a short amount of time with the lesser water profiles that need less of a concentration of ions, it was actually okay. The energy output consistency we hooked up to our motors running sequentially, and what we found out was that the voltage and the current that we needed was much less than we thought, but also the voltage was much less than we thought. So it wasn't within a 5% difference, but it's still low enough that we know that we are going to be able to run these things at a relatively consistent rate without having to worry about too much of a draw on our power supply. The flow rate, we operated our pumps in 30-second intervals. Again, we did some testing on this. The results are still inconsistent. And we ended up brewing 1-gallon batches to extrapolate for an 8-gallon batch. And we got about 20 minutes of time, which is about twice as much. But we also used the most concentrated water profiles since we were only using a 1-gallon batch. We wanted to make sure that we had something that we could actually measure. And again, the only thing that we were able to test was the calcium. So we also just wanted to make sure that when we actually were running a complete system, with good motors and pumps that were able to deliver exactly what we wanted to, the operation time, we should get a better estimate of how long it should run. But these are our partners. They were kind of our advisors, our industrial advisors, as well as helping us with some supplies. Of note, Franklin Winslow and Sherry Henneborn. Franklin Winslow of the Yards Brewing Company here in Philadelphia, and Sherry Henneborn of the Water Department of Allentown. All right, thank you very much for watching our presentation, and I hope you enjoy.